So by recognizing that each of those colored triangles shown here is a right triangle in a three-dimensional space, the following trigonometric relations can be established. So shaded in light blue, we have this triangle here. Now on the surface, if you're just looking at this, straight on, that blue triangle does not appear to be a right triangle. However, when you realize that this is a three-dimensional space being represented here, then yes, it should become clear that this blue triangle is in fact a right triangle. You have to imagine looking at the blue triangle sort of from this perspective, looking at it face on from this perspective. So here, this is the right angle. Of course, it doesn't look like a right angle because it's a three-dimensional space being represented on a two-dimensional screen. But this is a right angle of that right triangle, which means this side opposite of the right angle is the hypotenuse. For the red triangle, the same thing is true. This side, vector A, that line, is the hypotenuse of this right triangle in red. And for the triangle in green, that right triangle, here's the right angle. And so the side opposite of it is vector A, the side that has magnitude A. So now we've established three different right triangles in this three-dimensional space. So we can set up our cosine relationships: cosine alpha, cosine beta, cosine gamma. So from the blue triangle, cosine alpha is adjacent over hypotenuse, scalar magnitude of ax over scalar a. Cosine beta, adjacent over hypotenuse for the red triangle, that would be ay over a. And cosine gamma would be adjacent over hypotenuse for the green triangle, that would be az over a. These dimensionless values are called the direction cosines of vector A. Note that in general, any vector can be expressed as the magnitude of that vector multiplied by a unit vector that defines its direction, such as vector A here would be equal to the scalar magnitude of the vector A times the unit vector u subscript A. Therefore, an expression of unit vector u sub A for any general vector in 2 or 3 dimensions is as follows. U sub A vector equals the vector A divided by the scalar magnitude A. So that would be the vector A, which we already know can be expressed as axi hat plus ayj hat plus azk hat, all divided by the scalar A. So each of these terms gets divided by the scalar A. So the unit vector u sub A can be expressed as the scalar ax over a times the unit vector I hat, plus the scalar ay over a times unit vector j hat, plus the scalar az over a times unit vector k hat. Now we have a summary of important relationships regarding three-dimensional vectors, and those are as follows. So first thing is that u sub a unit vector can also be expressed as you see here, cosine alpha I hat plus cosine beta j hat plus cosine gamma k hat. Also, because any unit vector always has, by definition, a magnitude of exactly 1, then the sum of the squares of the components of the u sub a vector must equal 1. So we have another important identity where cosine squared alpha plus cosine squared beta plus cosine squared gamma must equal 1. And then furthermore, vector A, any vector at all, can be expressed as its magnitude times the unit vector in its direction. Okay, that would also be equal to scalar A times cosine alpha I hat plus scalar A times cosine beta j hat plus scalar A times cosine gamma k hat. That equals scalar AX times I hat plus scalar AY times j hat plus scalar AZ times k hat. Regarding addition of vectors using the component method, we can extend what we've already learned about adding vectors using the component method from 2 dimensions now to 3 dimensions. The component method is used to add vectors in 3 dimensions. Once each vector is resolved into its components, the respective xyz components are added to determine the components of the resultant vector. So our resultant force, that we often denote as F sub r, is by definition the summation of all forces present. So that would equal the summation of F sub x, which is the summation of the x components of forces multiplied times I hat, plus summation F sub y times j hat, plus summation F sub z times k hat. And remember, anytime we have a vector expression in which we're using the unit vectors I hat, j hat, and or k hat, this is called a Cartesian vector expression.